Hello everyone, welcome back. In this particular video, we're going to focus on the directing effects of multiple substituents. So this is when you have more than one substituent on an aromatic ring. And we're going to use the example of benzene derivatives here. So what we're going to examine is how do multiple substituents affect the electrophilic aromatic substitution in terms of the regiochemical outcome of the product. Where would the electrophile end up in the product? So let's look at a few different scenarios here. The first scenario that we're going to talk about is where the different substituents, they reinforce directing effects of each other. So when we say each other, we are talking about directing effects here. So there's more than one substituent and their directing effects are reinforcing each other. So the first example that we are looking at is the chlorination of this methyl sulfonic acid, sort of. So we have a para-toluene sulfonic acid, to be very specific here. So there are two substituents here. We have the sulfonic acid and we have the methyl group. Now, what we know is that the sulfonic acid is meta-directing. This is meta-directing. It is a strong deactivating group. It is strongly deactivating. So the sulfonic acid group here is strongly deactivating, and it is meta-directing. Now, so the sulfonic acid group here would like the incoming electrophile to go to one of these meta positions. Okay, that's where it would like the chlorine to go. Now, the other substituent that we have here is the methyl group, which is a weak activator. So it's weakly activating, and it is orthopara directing. So it's a weak activator and orthopara directing. So that means it wants the incoming electrophile, which is the chlorine, to go to the ortho or the para positions. Now it is ortho and para with respect to this methyl group. So ortho with respect to the methyl group would be these positions. So the methyl group is also directing the chlorine to those positions. And para with respect to the methyl group is going to be this position where the sulfonic acid is. So that position is already occupied. So in this particular example, what we notice is that both directing groups are reinforcing each other's directing effects. The sulfonic acid is directing the incoming chlorine to the meta positions, and the methyl group here is directing the incoming chlorine to the ortho positions, and the meta and the ortho positions with respect to these two groups coincide. They are the same. So essentially, when we do this reaction, we are going to get the product where the chlorine is going to end up on the meta position. So that will be our product because both groups reinforce each other. Now, let's look at another example. We have three substituents here, and we can just think about a general electrophile. This reaction, this compound reacting with some electrophile. Where would that electrophile go? Doesn't matter what the nature of that electrophile is. So if we examine the different groups that we have the nitro group here and a nitro group over there. And what we know is that the nitro groups, these are strong deactivators, and these are meta-directing. So as far as the nitro groups are concerned, if I consider one of these nitro groups, what I notice is the other nitro group is meta to that nitro. So there's another meta that's open, which is going to be here. That's the meta, which is open because the other meta is occupied by the nitro group. And if I consider the second nitro, we have a similar situation. The other nitro group is meta to this nitro group, and then the open meta position is here. So we basically, both nitro groups are going to direct this electrophile to this position. Now, as far as the methyl group is concerned, the methyl group is a weak deactivator, and it is ortho-para directing. So as far as the methyl group is concerned, it would like the incoming electrophile to go ortho to it or to the para position. And what we notice is that both ortho positions are already occupied by the nitro group. So there isn't an open ortho position. So the only possibility here is for the methyl group to also direct the incoming electrophile to this position. And so what we notice is that essentially the three substituents on this benzene ring, they are directing the incoming electrophile to this position, which is meta to both nitro groups and para to the methyl group. So our product from this reaction is going to be have the electrophile at that carbon. So this is what we are going to get. So that is the first scenario where the various substituents are reinforcing each other in terms of their directing effects. We're going to look at the second scenario here now. Now, the second possibility is that we have multiple substituents and the substituents compete with each other. They're not directing the electrophile to the same position. And what happens in such a scenario is that the more powerful activating group dominates. Okay, so that's important here. So the more powerful activating group dominates under such a scenario. Let's look at an example. So we have this nitration reaction of this methyl and methoxy substituted benzene. So if we look at this particular molecule, we have two directing groups, the methyl and the methoxy group. The methyl group is a weak activator, and it is ortho-para directing. So the methyl group would want the electrophile, which is the nitronium ion here, to go to the ortho or the para positions. So the methyl group is directing the electrophile to the ortho positions or to the para position, but the para position is already blocked by the methoxy group. The second substituent that we have here is the methoxy group, and the methoxy group is a strong activator. It is also ortho-para directing. So as far as the methoxy group is concerned, it would now try to direct the electrophile to ortho positions to it, which would be these positions, or the para position, but the para position is blocked, so the electrophile cannot go over there. Now, among these two groups, so since the methoxy is the stronger activating group here, its directing effects are going to dominate, which means the incoming electrophile would go to the positions that are ortho to the methoxy group. So the product that we get from this reaction is going to have the nitro group, or is going to bear the nitro group at a position that's ortho to the methoxy group, because it is the stronger activator here. Let's look at another example here. Now we have a molecule that's tri-substituted. There are 3 different directing groups here. Let's consider them one by one. We have a hydroxy group, we have a methyl group, and then we have the nitro group here. The hydroxy group is a strong activator. Okay, so this is a strong activator. Ortho para directing in nature. Then we have the methyl group, which is a weak activator. Again, ortho para directing in nature. And finally, we have the nitro group, which is a strong deactivator, meta directing in nature. So the hydroxy group would want to direct the incoming electrophile to a position that's ortho to it. And notice that one of the ortho positions is open, while the other ortho position is blocked by the methyl group that's already substituted. And so is the para position with respect to the hydroxy. The para position is also blocked because the nitro group is at the para position. When we go to the methyl substituent, one of the ortho positions is blocked, but the other ortho position is open, and so is the para position. So those 2 positions are open with respect to the methyl group, one ortho and one para, and the para position actually. And now the nitro group is a strong deactivator. It wants to direct it to the meta position. So meta to the nitro group is the methyl group here. So one of the meta positions is blocked, and the other meta position is actually here. So that coincides with the ortho position, for the hydroxy group. So we have 2 groups that are trying to direct the electrophile to the same position. But as it's mentioned here, the more powerful activating group dominates. So the electrophile would go here because of the hydroxy group, because that's your stronger activator. This matters. And this is where our understanding of what's an activating group and what's a deactivating group comes into play. Because remember that an activating group is something that is trying to speed up the reaction. It wants the reaction go faster. It makes the reaction go faster. Whereas a deactivating group is slowing down the reaction. It makes the reaction go slower. So since the hydroxy group here, or the hydroxyl group here, is a strong activator and it's ortho-para directing, it determines what the product is going to be or where the electrophile would go. And so what we're trying to say is, if this compound were to undergo any electrophilic aromatic substitution, the electrophile would end up at the position that's ortho to this hydroxyl group, because that is the favored position. So this is the favored position here. So the electrophile ends up at that position. In this portion of the video, we're going to consider some steric effects that could come into play in an electrophilic aromatic substitution reaction. Now, what we know from prior discussions is that when you have a bulky group on an aromatic compound. And if you try to do an electrophilic aromatic substitution, we are considering a nitration here as an example. Then we have two possible products that can form. And the third butyl group here, this is an activating group, a weakly activating group. It is ortho-para directing. So the third butyl group is going to place the electrophile either ortho or para to itself. So there are possibilities where the electrophile could go here, or it could go here, or it could go there, if you're considering just a mono electrophilic aromatic substitution reaction. So our possibilities for the products are that we can get the electrophile, which is the nitro group, at the ortho position, or we can get the electrophile at the para position. Again, ortho and para with respect to the third butyl group, that is our directing group. And in this particular case, whenever you have sterically bulky directing groups, what we observe is that the ortho product is often the minor product. So this is our ortho product, while the para product is the major product. And the main reason here is that in the para product, we are able to avoid some of this steric strain that's developing here. In fact, we're able to avoid all of the steric strain that's possible in the ortho product. So the para product is favored over the ortho product. Now let's look at two sort of subsets of these sterically bulky directing groups. And we're going to consider a 1,4 disubstituted aromatic. What that means is your substituents are at carbons 1 and 4, or they are para to each other already. So if we consider a molecule like this, where we have a third butyl substituent and a methyl substituent, and we're trying to do a nitration on it. So now recognize that our third butyl group is activating. So it is ortho-para directing. So it wants the electrophile to go here, or at the para position, but the para position is already blocked because there is a methyl group here. Okay, so there is a methyl group here. And the methyl group is also activating and ortho-para directing. So it would want the electrophile to go ortho to itself or to the para position, but the para position is blocked. And since these are both weak activators, there is no dominant effect over here. So sterics comes into play. So our possibilities for the products are when the electrophile is ortho to the third butyl group, which puts the nitro group at carbons 2 or 6, which are ortho to the third butyl group. Or the other possibility is where the nitro group, which is the incoming electrophile, is ortho to the methyl group. So those are our two possibilities now. And in this particular scenario, again, the product where the nitro group is ortho to the less bulky methyl group is favored over the product where the nitro group is ortho to the dithird butyl group, because this particular molecule has steric strain in it. Okay, that's going to unstabilize the transition state that leads to the formation of that product because of the sterics that build into the transition state. Another scenario that we're going to look at is 1,3 disubstituted aromatics. And again, we're considering two alkyl groups to keep the strength of their directing effects the same. So we have substituents that are meta to each other or 1,3 to each other, 1, 2, and 3. So the two substituents are meta to each other. And so in this particular case now, we have a few possibilities here when we do the electrophilic aromatic substitution. The third butyl group would want the electrophile to go ortho to it, or para to it. The methyl group would want the electrophile to go ortho to it, or para to it. So we see that all of these positions sort of match. So we have three possible products here. One is where the incoming electrophile is between the two substituents, the nitro group in between the two. So that's ortho to both of them. The other two would have the nitro group ortho to the methyl group and para to the third butyl group. Or a third possibility is that the nitro group is ortho to the third butyl group and para to the methyl group. So all three products are possible here. As it turns out, this product here, where the electrophile goes between two substituents, this is always like the least possible, okay? This is the least possible product because there is sterics in both directions here. So there is sterics here and sterics on the other side. Now, between the other two products, when the nitro group is ortho to the third butyl group, this is going to have more steric strain compared to the situation where the nitro group is ortho to the methyl group. And so essentially what happens is this product here is our major product, and this is minor, and this is the least possible of the scenarios. Often this product is not observed under these conditions. So I hope you like the various scenarios that we have explored here, which might affect the outcome of an electrophilic aromatic substitution reaction. Bye.